Yeah. So machine learning as what its benefit to civil engineers or structural engineers or design engineers, maybe water and hydraulic engineering, is to use this as a surrogate model. So what surrogate model means, mainly approximation of a complex system that you need to use a significant time or effort to solve. So instead of that, the machine learning model, the machine learning model can be used to surrogate this by obtaining these solutions or whatever you require within a very quick time. So let me give you one example. So imagine if you are calculating the wind pressure on a tall building. So I'm talking about the time dependent wind pressure, not the average wind pressure or the equivalent static wind loading, which is governed, which is presented in existing design standard. So for now, most of these design codes uh, are not applicable beyond 180 meters uh, tall build, above 180 meters tall buildings, or their aspect ratio in plan larger than 6. So either we need to go for a wind tunnel test or maybe numerical modeling in the form of computation fluid dynamics. So these methods can take days to weeks. Just imagine if you are in a design, maybe meeting with a client. So if the team asks you, what's the wind pressure or what's the peak pressure on this building? So you can't say, okay, I'll do a wind tunnel test and get back to you. So because of these constraints, the proper wind engineering design, the modeling of unsteady wind pressure has been kept a really tight window during the design stage, just because it takes time and effort and resources. So imagine if we can develop a machine learning model that knows how this pressure on the building changes with time and changes with the geometry we give it to the model. And we can use it to simply predict the pressure on a building within seconds. So from your end, you only need to provide the geometric ratios of the building, maybe the wind angle, the locations that you need the pressure, the terrain conditions, wind speed, and etc. So the model will give you the pressure on it within seconds. So another application is when you are optimizing your design or structural layouts. So this is a recent study that we have done, and we have shown that using machine learning models to optimize these buildings or the reinforcement layouts can really save 10 to 45 percentage of material compared to the conventional designs. Because as we all know that what we take a panel, a critical element, and we mostly use a regular spacing for between the columns, unless it's different. So in this case, we are only providing the layout, and we let the machine learning model to come up with the layout itself with the primary beams and the secondary beams. So in this method, we could not only design but also save the material, which in turn save our cost. And then if we consider the machine learning model, so it resembles with something. It's just like a baby. So what you taught to the model will be obtained to you. So for example, if you teach a baby okay, this is a car. So whenever the baby sees a car, he or she knows that, okay, it's a car. Even if you show a van, the baby has only been taught by showing cars, so he will figure out it's a car. It's another type of a car. That's it. So when the baby learn colors, okay, with time he or she knows that, okay, this is a red car or maybe a yellow car. Likewise. So the machine learning model also will only give you a solution or else a predictions only based on the data it has been trained. So that's something you need to make sure. So if you, let's say, you trained it using x values from 1 to 10. If you have trained your model for the x values, let's say x is the variable from 1 to 10, so it cannot reliably predict for x values more than 10. So that's very simple. So why we need or the towards machine learning approach? Just imagine I have taken this example as how the compressive strength data varies with the time or its age. So you all know that it will take a variation like this. So the blue color shown here is the general trend that you see as a relationship, but we don't know its equation or the actual relationship. So if you are developing a machine learning model, that should be able to predict its compressive strength based on the age. So if you are giving this age as an input, the model should give you the corresponding compressive strength. So the simplest model that we can use for this task, uh, let's go with that one more time. So we have data called, let's say, I'll call this in order x1, x2, sorry, x1, y1, x2, y3, x2, y2, x3, y3, and so on. So I hope Dr. Nihaj covered training and testing. So I'll anyway go through these again. So just because we have a bunch of data, we can't give all these data to the model. We choose some of its portion as training data. Using those training data, the model learns. In this case, we have these blue color dots. We have these blue color dots, which are training data. So these are the data points that we give to the model. Okay, learn the pattern of these data. And we keep these green color dots hidden to the model. We do not show them to the model. We use them later to evaluate the model. So all these points have x and y coordinate. Okay, is it clear to you? Clear to you all for now? Or do you have any questions?
It's clear.
Okay, so it's okay. I have now used all the training data points, or else I have extracted only the training data points which were in blue color. So the basic machine learning, the most basic one we can use is the linear regression that we already know. So even if you use Excel, we can develop the best fit line, which is the linear regression in the form of y equals mx plus c. But you would notice something. Doesn't matter how we change the slope of this line, we will never be able to match the exact variation of these training data. So you can see I had changed the slope of the red color line. So here it's a relatively lower slope and here it's a high slope. Doesn't matter how I change it, it's never gonna approximate the actual variation, which is slight of a curvy behavior. So, so this straight line is not flexible at all and does not replicate the actual relationship, but it has a certain relationship with this training data. That's the maximum the linear regression can do for us. Imagine a squiggle like this. So the squiggle line goes, even we can train to go exactly through the training data at each point. So if I ask you a question, what do you think is the best model? Is it a straight line or the squiggle? So the squiggle is super flexible and goes through all the training data points. What do you think is the best model um, for now? Anyone? Okay, someone saying straight line. Anyone else? Squiggle line. Okay. Okay. Now, let me explain. So, we only use training data. Okay. So, these are the points that we gave to the model, learn the pattern. We have testing data as well. So, if we go ahead, now, if you compare these two models, now, this is the linear regression model. So whatever the x value, so let's assume this is x1. So the original x value is x1 for under this blue color dot, and let's say its corresponding y value is y1. So the prediction is close. It's okay. But for this case, let's imagine it's x2. So the linear regression model gives you a slightly higher prediction compared to the original y value, which is, well, let's say y2. Um, Here it's the other way around. So the linear regression under predicts the actual y3 value. So this is x3. So this is original y3 actual value, and this is the predicted y3. So we call this the predictions obtained from training data. Even when you have developed a machine learning model, it will give you sort of prediction for the same training data as well. But in the squiggle, you will see for all the x values, it will give you the original y value because this squiggle has gone through exact training data locations. So, so this is one of the fundamental concepts in the machine learning, which we call bias. So models like linear regression, which is unable to capture the actual relationship. Okay, so we call it, so the bias is high. Where in the case of squiggle, it has very little bias because it hugs all the training data points. So in this case, this is low, very low bias. This is relatively higher bias. Is that clear to you all? So I can't see your chat. Yeah, you can even use the chat, but is that clear to you all? Yeah, someone saying he can't hear me. Am I audible?
You are audible, sir.
Yeah, okay. Let's go to the next slide. And now this is the important case that we need to design what's the best. Now we plug all the testing set. Okay, so green color dots are the testing sets. So now what happened? Linear regression developed so far has obtained a good predictions even for the testing data. Why I call that will be shown in the next slide. And the squiggle, if you can't say whether it's good or bad, let's wait. Okay, let's see what will happen with the testing set. So now we are going to isolate only the testing data. Okay, so as I told you earlier, so whatever the x value given, all the prediction will lie on this linear model, and all the predictions will lie on this squiggle. So the distance between the prediction point on the line and the actual y value, we can call it as the error. It's basically the ith prediction minus ith actual. Okay, so since these predictions can be or the error can be negative or positive, when we add them, they can cancel out. Because of that, what we are going to do is we square them. So it's always positive. Doesn't matter the predictions are under predictions or over predictions. And we take the summation of those error terms, we end up with sum of square error. So if you consider the sum of square error for these, now you can see what model is the best. What do you think is the best? Now, is it still squiggle or the straight line? You can, I mean, you can't quantify it, but approximately having look at the dotted line and their length, you can reasonably approximate their sum of square error. What do you think is the best? Yes, yes, yes. I'll come to that point. Someone uh, explained it very well. Um, Still saying squiggle line. Someone saying squiggle line. May I ask what's the reason that you said squiggle is the best? Maybe. Yeah. No, it's good. So you can see the sum of square of errors is higher for the squiggle. The reason was the squiggle tried to fit into exact training locations. So it has very low bias and very high variance for the unseen data. But in the sense of linear regression, it has a higher bias, but it didn't exactly fit into all the training data as it is. So it will be reasonably good for even unseen predictions. So we call this the second most basic concept. So before that, we call this term as overfitted. So the model is overfitted to training set and do terrible job when predicting for unseen data. So we call this the model has a very high variance. So just because it's very well fitted to training data, it shows poor performance on the unseen data. So it has high variance. Now, if you look at the straight line was high bias and low in variance. So this means the straight line consistently give good predictions, but those are not great predictions. On the other hand, the low bias and high variance, the squiggle, something like a squiggle, so fitted exactly to training data. So this can perform well or worse. We don't know for future or unseen data. So then, what do we need exactly in machine learning? So what happens something like this in the case? So imagine in your training data, you didn't notice there was an outlier or there was an erroneous reading. You didn't know that it was there originally. You go ahead and trained your model. So now your squiggle even fitted to that outlier as well. So what do you think? Is this good or bad? So green color ones are testing data. What do you think about this model? Yeah, it's a bad model. So obviously, in during this region, the error will be so much high. So this this is really observable in machine learning when you see the models with high R squared values for training and very low, significantly low R squared values for testing. So even some of the articles say, okay, we have achieved high accuracy, but it's actually not. If you see R squared 99%, now you need to be careful. It's not actually can be accurate, but the model actually have overfitted. So you need to know accuracy is closer to 99 or 100. It's something you need to be really careful. This can happen actually. The model has not learned the actual pattern, but instead have overfitted to something else or maybe another relationship within the existing within the data. So once you plug the testing data, model will give you a poor performance. Is this clear to you? Is that clear to you all?
Yes.
Okay. Any questions you have up to now? Okay. So overall, and finally, what we need is find a machine learning model which has a low bias and low variance. That should be our target when developing a good machine learning model. Not to fit into extreme, exactly to training data, and not to not to give a simple relationship rather than the actual, which has a higher bias. In this case, which have high variance. So we need something like this, as you can see, which will give you a greater predictions for even training set, and as well as it maintains the same level of performance for the testing data as well. So this is often we call as a bias and variance trade-off. in machine learning. So, okay, we'll now jump to an example. I hope you all have downloaded the data set I have given you. So it's mainly the UCI compressive strength data set. So there are a bunch of variables. These are the inputs and the outputs. Let's go. Wait a minute. Let me explain. Now, first, we'll move to Jupyter. Have everyone installed Jupyter? Is that working? Or anyone needs help? Has everyone installed Jupyter? Is that working? Okay, one said okay. So can you open Jupyter in that case? Let me go to Jupyter as well. But before that, I'll explain few points. Yeah. First, I'll go to Jupyter. Okay. Can you see my screen? The Jupyter notebook?
Yes.
Okay, great. So I have commented most of the places so that you can you know where to change and um, what to be done. So this is the data set and it had um, compressive strength data and these were the input values they suggested. And mainly we'll be using Jupyter Notebook to figure out how to process data and how to fit a model in this case. So first, this this first line is mainly for the libraries that we need for these operations. So libraries like pandas. So those are to handle the tabular data. So you can see this, I'm importing pandas library as PD. So whenever you see something named as PD in a later code, that means pandas. So I'm importing NumPy as NP. So likewise, I'm importing. So this matplotlib and Seaborn are mainly for graphics, like you want to plot something, and especially Seaborn has very nice color palettes, and matplotlib does too. And it's good practice to call all these libraries beforehand. I usually do it because, and then for later cells, you don't need to call that library again. Say, for example, if I have a model like this, let me show you. So you can see I have, so it's just, sorry, this is linear regression model. So I have import that model over here. But usually if you are just developing a linear regression model, or if you ask ChatGPT to develop that code, so that will give you the code from the initial importing itself. So here you will see I haven't imported anything from sklearn. So it's because I have already done it in the first cell. So make sure you call all the libraries that you need uh, beforehand. Sometimes when you run this code, you will get an error, something like this. At the end of the error, you will see no module named as pandas or something with that name. So that means you don't have that library installed. So what you need to do is, don't worry, go to the start bar, go to a command prompt, I mean the terminal, type there. If you get an error like this, you just need to type pip install pandas and hit enter. That will do the job and install that library. Again, you can comment run this cell and see. If there's no error, then it's okay. But sometimes, rarely, I have seen people who have latest Python versions have some issues with running the codes. That's mainly because later versions, maybe NumPy or Pandas or later version of Python can be incompatible. In that case, you need to downgrade it to a stable version. So I hope you did not come across some issues like that for now. If anyone has, just let me know, okay? So these are the essential libraries I have imported, okay? And then we'll teach these ones later. First, let me take you through how we open this data set in the Jupyter notebook itself. So I'm using I'm giving a name to that data frame as df, or else you can use any name. We can call it data. Okay. So df. So I'm using pandas library as pd. This is the command to read the CSV file, which is in concrete CSV. So this is in my same working directory. But if it's in a different subfolder, you can give the exact subfolder location here as well. That works as well. No, nothing to worry. So once you give that, so if you run this one, what will happen is, so it will read the CSV file and save configure that as a data frame. So if you want to see that data frame, so just type df and you will see what's there. So this has 990 rows and with nine columns. And if you need to see the columns, what are the column names, you can just type columns till it will give you what are the columns that it have. But if you, let's say you need the descriptive statistics of these columns, for that, describe, I think that's the code. Yep. That will give you mean, count, and standard deviation, and quartiles, and everything for each variable. In this case, you can see the compressive strength that goes from 3 megapascal to 68. And the age of the concrete goes from, I think, 1 day, it should be 1 day, to even 1 year. Yeah, 365 days. So it's always, you should look at all the variables before selecting all these as inputs, because there can be inputs which are constant throughout the dataset. So let's say someone has done all these mixed design by keeping coarse aggregate as a constant. So having included it as an input in the model doesn't make any sense, because It has no impact because it's a constant throughout the entire data set. So you need to check these descriptive statistics at the first go. What are these data? What are the statistics of these data? That's a good practice that you should have. And then, is it is do I want to repeat myself again, or is that clear to you? Are you doing with me as well? Sorry, I can't see the chat.
Excuse me, sir.
Yeah, go ahead.
Sir, can you repeat how do you open this Jupyter window first?
Okay. So I'll close this everything. Can you see my screen? There are files like concrete, day two session. Can you see that
Yeah.
screen?
Yes,
Yeah,
sir.
okay. So this is my code and the data file. So what I simply do is just open a terminal from here, or else can you do that? Can you do it too?
Yes, sir.
Yeah. So once you do it, just type Jupyter Notebook. What I typed was visible to you,
Yeah.
and press enter. That will open the notebook. All good? Were you able to open it?
Oh, yes, sir. Okay.
Yeah, okay. So we'll go to the code. So there are a couple of options like file. Mainly you can download this as a PDF file as well. So I'm explaining again a bit of these things. And latex file or PDF. And then you can save it and cut cell and cell operations basically. And if you want something, so for example, if you need to something as a note, not as a code. So this cell, what I have done is I have saved it as cell type is a markdown. So it's not a code, it's a markdown. So whatever essential notes I have in here, but if I need to change it as a coding cell, I will just go back and change it as a code. And this kernel, well, you need to restart and shut down or interrupt whatever. If it's something stuck, you can use this. And if you need to run all these cells, you can just click run all, make sure there are no errors. Or else what I usually do is run each cell at a time. So that's easy. That's the main difference between Jupyter and Python, because Python, um, you can't run each of these codes line by line. Here you can compile them cell by cell and run it. So, which is why we are using it instead of Python. Otherwise, it's the same thing. Is that clear to you? how to open the notebook and run it. So for example, even if I run this one, nothing happens. So then I'll go to the first column and run it. So you can see it's a star sign. So that means it's running currently. So it's importing all the libraries. Yep, that's done. And then I will go ahead and load my data set. And I described it. So first few important points, you open the data set. So this is to open the CSV as a data frame. So if you want, you can change any of these names, but make sure you call them correspondingly in the later cells as well. So now, once I check the statistics of the data, what I usually do is I check their correlation, mainly using Pearson correlation. So I can use this correlation matrix. So I'm using the data frame, this correlation function, to get the heat map. So this is SNS means, if you remember, which I have called as Seaborn. So it's a library. I'm calling the colors and everything. So if I run it, so that will be like this. So there are many color palettes. So I don't remember their names, but I think I have given the link. So if you go to this link, you can check what are those color palettes. So if you need to reverse this color palettes, let's say you need maximum to be black and minimum to be white. So you just simply, you can just reverse this by typing underscore and R. Yep, can reverse it. And line width and everything. I have given mostly that you can edit this one. And if you need to change the plot size, you can change it as it is over here. Let's see what will happen. See. So the main reason I wanted to show this is, if you are developing a machine learning model, first, it's good to check their correlations. See, in this case, I'm trying to predict the compressive strength. Okay. So all these variables are inputs. So now you can tell me if this is this a supervised learning or an unsupervised learning? Anyone? Okay, one set supervised, others. Okay. So the reason I brought this to you is, look at the correlation. So this is showing the Pearson correlation. So it's that linearity between each pair of variable. So if you have a look at compressive strength and especially the cement content, it has 0.46. It's not, it's a moderate correlation, but if it goes beyond zero point 0.6, which is a good correlation, and if it goes beyond zero point 0.8, and it's a strong correlation. So if you have strong correlation with the target target variable. So in this case, maximum one is 0.46, and over here it's weak 0.34. No, none of others showing any sign of high, maybe negative or positive correlation. So correlation means if one changes, let's say when x increases, or else when the variable 1 increases, the variable 2 will increase as well. So that's we call positive correlation, and it's very strong when it is closer to positive 1. And it's on the other side, let's say when one variable increases, other goes down, or else other variable decreases, we call it negative correlation, and where its strength mainly determined by the magnitude. If it is close to -1, it's strongly negatively correlated. So usually if there are variables which is correlated with the target prediction, the compressive strength, more than zero point 0.6. Let's say there was a variable, it's having zero point 0.7 correlation. So you don't need to go ahead and jump into a very complex model. The reason is there's one variable already having a good correlation. So most of the time, a simple model like linear regression or else polynomial regression, maybe decision tree, will give you a reasonably good prediction. Okay. So what you need to know is in machine learning, you need to use the simplest algorithm that gives the best accuracy, not the most complex accuracy. Let's say you want to, it's like this. If you want to dig a hole in your backyard, you can either use a shovel or else you can use a backhoe. So you don't need to go for a backhoe when you have a simple shovel and dig that hole. So it's like that. If the problem is less complicated, use a less complicated model. Not, you don't need to go for an ANN all the time. If the linear regression works, let it be. If that doesn't, then go for a more slightly advanced model and see. So first point, you need to check the correlation between all these target prediction and their inputs. If there's a correlation, you need to make sure, okay, I have a variable which is very well correlated, so I might not need a very complex model for this. And this is not universally true, because there can be a variable which is non-linearly correlated to the compressive strength, because Pearson correlation only showing you the linearity. And there are matrices like Spearman correlation which shows you non-linear correlation as well. So this doesn't mean all the time uh, there are no other correlations. There can be, but you need to make sure and you need to investigate and take a bit of the time with the data and investigate what are these data just before jumping into the model. And another point is check the correlation between the inputs as well. There can be inputs which are correlated very well. So that means one input is maybe dependent on the other input, or else they are not actually independent inputs. In that case, best is to remove one of the inputs if you really don't need them, or else uh, we need bit of feature engineering part to develop a new feature, or else what to go with ahead. But in this case, luckily we haven't got such strong correlation between input pairs other than, yeah, super plasticizer. There's a moderate one. I mean, I would say fairly good super between super plasticizer and water content. So you know why, right? Already. So this means, I would say, if you consider all this data set overall, when when the water content increases at certain mixes, the super plasticizer content has been reduced. Oils, the other hand. So other than this minus 0.66, you can see between super plasticizer content and fly ash as well, 0.42. It's not that even, I would say, moderate or weak, towards weak. So if something goes more than zero point 0.8, then you need to worry actually. So that means those are strongly dependent inputs. Having those inputs in a model can really complicate the model because if you want to check the model sensitivity, let's say how this variable impact to the output, then you have a bit of trouble. Just keep that in mind. Again, overall summary, you need to check the statistics, you need to check the correlation, especially with the target variable and the inputs and between the input pairs as well. Once we do this, uh, yeah, so you don't need these rows. Even you can develop new input pairs as well. So in this original data set, I didn't have water to cement ratio feature. So I developed data frame. So if I do this, it will give you to cement ratio or maybe WC. So that means data frame, I'm taking the water column divided by data frame, I'm taking the cement. So that will give you a new feature. Oh, sorry. Yeah, that will give you a new feature, water to cement ratio, which you can either use it as an input in the model or else leave it as it is. So it's up to you. You can always modify these columns or maybe add two columns together or maybe subtract one column. You can all do all these operations inside Jupyter other than you would be doing in an Excel, these things. It's very easy once you are familiar with Jupyter because this is only for 990 rows. Imagine you have a 1 million or 20 million data set. You wouldn't be even open the Excel sheet. But still, Jupyter does it for you. So you can always rely on Jupyter and open these large files and see what's going on. If you want to modify anything, you can do it. You can even sort it. You can even plot anything and see. So this is to get, so the next row, so df info means the data frame I have defined its information. So basically data types and they are floating integers, uh, because sometimes these data, it has happened to me one time. So I saw these were numbers, but when I fit in the model, there was a D type, something called D type error or something. I couldn't figure it out why, because I saw it was a number, but I couldn't figure it out why it can't use can't be used in the model. Then when I check the data type, it was not a numeric value, it was a string. So you need to make sure these you check all these data types as well. Otherwise, you would be spending so much time trying to figure out what's going on with the model. So again, the same thing, I would delete this one because we have already done. Now, let me go back to the presentation really quick. Share. Can you see my presentation?
Yes.
Okay, all good. So now we know what are these libraries and everything, why we need this. I have given every detail in the notebook as well and over here as well. So NumPy, these are for the calculations, and Seaborn and Matplotlib for the plots and charts. Scikit-learn is mainly for machine learning models, and some of machine learning models. I mean, I would say most of the machine learning models are available in scikit-learn. And TensorFlow and Keras are for deep learning that will not be touching today, but in a later day. Now, we define this as a supervised learning model. So we know the difference between supervised and unsupervised. So supervised means inputs and outputs are, we have inputs and output label data we are working with. We know what are the target, we know what are the inputs. And in supervised learning, in especially civil engineering applications, we'll be using regression and classification. So regression means we are prediction is a continuous value. Something like elast. So we have inputs like length, diameter. Let's say we have uh, steel columns. We know their length, diameter, modulus of elasticity, and support conditions, and etc. And we are going to predict the elastic buckling load, which is a continuous value based on these parameters. And for the classification, your prediction is, I mean, it's very similar. Only what you are changing is the prediction, which is a class. Now you are predicting a class like failure mode, whether it's failed by yielding or whether it's failed by buckling or maybe the fracture. So I hope you have done these, done these things yesterday. Maybe Dr. Mihach might have introduced to you. So very good example for classification is how you give the student scores. Say, for example, if you have obtained 75 to 100, it's a A. It's and then 50 to 75, it's B. So it's a class that you are predicting. Is that clear to you or not clear? Is that clear? Yeah, someone said, yeah, yeah, name PD is not defined. In your error, you can see, especially the last line, it's a name error. Name PD is not defined. So that means the notebook doesn't know what PD is, which was in our first line. We imported pandas as PD. So you need to run that cell and come to the second cell. Who's that? Ganathaban. I don't know whether I spell your name correctly. Can you do that and let me know? Can you still see my presentation or not? Hello?
Yes, we can see, sir.
Okay. Okay. So even there are occasions that we can use unsupervised learning. So it's simply we don't have a specific target variable. Say a data set like this. This was a part of data I copied from a bridge failure data set. So we had the bridge numbered from 1 to and so on, and then the system, whether it's an arch, suspension, or truss type, and then the material, timber or steel or concrete, and their span, and the age of the bridge, and the number of lanes it had, and the type of loading it got, and the state of that type of loading. I think it's the predominant type of loading that it got, mainly which caused the failure or maybe the damage, and then the state, whether it's a collapse or no collapse. So in this case, we don't have a specific target output. Let's say someone wants to cluster it. That means we need to extract a pattern in this one. Let's say someone see a pattern like this. Okay, if the age is more than 50 years and span is more than 60 meters, which is made from timber, which is susceptible to uh, collapse mainly because of fires. Something like a particular grouping can be done. We call clustering. So it's an unsupervised learning. We can extract local patterns within this data. So that's an unsupervised learning we can do, but we are not going to do in this example. But just keep this in your mind for your information. We can do these things as well if you have data. And then we went with the inputs and outputs. Now, this is for your additional information only. I mainly, so what you had is raw data. Before using it in the model, we need to process it and make sure this is clean, consistent, and structured and ready for the model. So for the cleaning process, what we can mainly do is to check whether there are missing data, or whether there are outliers, or whether there are duplicate rows. Data integration means whether there are duplicates or whether we can we can merge two sets of data into a single data frame. Let's say someone has compressive strength data and someone has flexural data strength of the same uh, mixed proportion. So we can merge those data into a single table. And data reduction, if there are unwanted variables, and maybe data transformation. So we'll be mainly using few of these for now, but these are for you additional information. There are lots of technique that we can pre-process. At the end, we need to make sure clean, consistent, and structured data to be used for the machine learning model, because the model doesn't know the quality of the data that you give. If you give bad data or if you give garbage, it will output garbage. If you give good data, it will give you good predictions. If you give a bad data, so does the model output is. And in this pre-processing, what I mainly did was this was the same data set. I think Dr. Nihaj sent you, but does anyone remember how much data rows that it had? It should be more than 1000. Does anyone remember that number? But mine only has 990. Yeah. The reason was, I'll show you. Where's the zoom? Can you see my notebook?
Yes.
Yeah. So again, I'm at pre-processing. So I checked for whether there are missing values. There were not. But you need to know what if there are missing values as well. So the easiest one is if there are few rows, let's say one or two, and if it doesn't impact your predictions or else the data set, the size, let's say you have 1,000 and you have only missing one or two rows, you can just remove them. No harm. But it depends on the context as well. Let's say you are someone working with rainfall and river flow data. So rainfall can be certain value for a period and then zero for some time and then again have peaks and lows. So in that case, based on the context, you can either fill it by zero if that's a point where is missing, which the neighboring parts has zero in it, you can just fill it from zero. Or else you can fill it with the average value of that variable. So all depends on the context and the where they are used. And the best one I'm suggesting for engineering cases is k nearest imputation. So just forget about the name. What it does is it see the neighboring points. Let's say there's a point, you know the cement content and water content and compressive strength. Let's say cement content is 300, water content is 100, you know the compressive strength. The next one is cement content is 310, water content is still 100, you don't know the compressive strength. So what KNN imputation or KNN filling does is just look at these neighboring values with it looks at the instances which are very similar to the missing instant and interpolate based on those instances. So I would commend this one. Just check KNN imputation, which is very good and logical. If you ever want to get, but having said that, it's strongly context dependent. KNN imputation sometimes cannot be useful. Maybe if you are working with hydrology data, so you need to check the data and their variation. So coming back to that, I will define my parameters as inputs. So we have cement, blast furnace, sag. If you need, instead of water and cement, you can remove those and get this feature as well if you need. You can do that as well. Just play it and see. But for now, I will use the original inputs. And the output is compressive strength. So the X values are the input values, input arrays that I'm using. So I'm calling from the data frame these columns: cement, blast furnace sag, and fly ash, water, superplasticizer, and coarse aggregate, fine aggregate, age. If there's an error, it should be mainly because of whatever the name here is not consistent with the name here in the Excel. One time it happened to me, the name was same. So I just typed age here. But I couldn't run this one. There was an error saying there's no feature called age. What happened actually was in the CSV file, after the age, there was a space. So the actual name was age with a space. So you need to be careful. That's why it's good practice before you get the before you type these inputs, just get the column names, df columns. So it will give all the columns. So you just need to copy and paste it here. That's it. Then there will be no confusions. And yeah, this is now y variable, which is compressive strength. And then I divided these into training and testing. As I told you, we can't use all these data for the training. So in this case, I have used X training, X test, and Y training, Y test based on the main XY test. So this was the operation I'm using. So you will see I have called this one in the beginning. If I'm not mistaken, should have done it. Yeah. sklearn, I have imported it. Otherwise, if you are just running that cell only, if you don't have those libraries, you need to import it here like this. Otherwise, it won't run. So here I'm using test size is 25%, but if someone need, you can go with 30%. It does make an impact on the predictions. Yes. It doesn't mean that if you use a higher training set, it will give good prediction for testing set. It's not. But generally, I have seen uh, zero point 0.2 to zero point 0.3 percentage going for the testing set in engineering research mainly. And if you don't have enough data to split, let's say you only have 100 data points. Now if you go for a 70-30 split, you only have 70 data points. So I don't think it's very good to go with a machine learning model other than linear regression or polynomial with 70 data points, or maybe a decision tree. So how to choose whether my dataset size is enough? There are no guidelines. I mean, hard guidelines saying that dataset should be like this, but sometimes we use these thumb rules, like number of data points should be at least more than 10 times the number of inputs, which is not a perfect one, but at least will give you some sort of an understanding. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So at 9 inputs, so that means at least the training sets should have 90 data points. In our case, we have 990, but someone can see this in a different way. Say, if one variable, okay, changes 2 times, and or at least this variable should change 4 to 5 times. So that means if he wants to change all these variables at least by 5 values, that will have large number of data points. But sometimes we can't satisfy that much of an amount. So just make sure you have enough data from the from the data sets I have used, I've experienced when we have at least around 1,000 or more than 3,000, our models are stable. But when it becomes less than 500 or 400, it's the models are becoming slightly unstable. Even if you train few times, the results will be different. So data set size does matter. So now going back to the original question, why I have 990 rows? So I notice this is something I do usually for the target prediction. So whenever I divided training and testing, so once I explain, I will give the break to you. So uh, when we define training and testing data, I usually plot their distribution. So you can see that this is the yellow color is the distribution of the testing data, and the blue color is the distribution of training data. So you can see, so those two distributions resemble. So we are mainly trying to predict this distribution. That's it. So this is where our compressive strength values fall. So training distribution is very similar to testing distribution, where we are going to predict later. We are trying to fit into training data and test using the yellow color data, which is fitted in this distribution. So if there's odd shapes, let's say your training distribution is like this and training testing distribution is something else, that you can't do it. I mean, you can't predict, you can't train to for a specific distribution and you predict some completely different distribution. So unless you see the distribution, you won't even notice it. So this is a common pitfall. You need to check the distribution of especially the target variable. And there are, in this case, it looks like a bell curve, and there are some distributions which are very hard to predict, something like a very high tail distributions. In that case, we need to either transform those data to different distributions. Say I have the compressive strength data, I take their log value, log compressive strength, so I change their distribution, so that something, so the obtained distribution is now somewhat fitable. And the other important thing is you need to check for the outliers. So in this case, what I usually do is I check the distribution from the, so you know that from mean, 1.96 standard deviation to the left and 1.96 standard deviation to the right, you will have 95% of the data. So I usually choose the data from lies from two standard deviations either side from the mean. Anything falls outside, I take as outliers. I usually remove them. That's what happened to the original dataset. When I checked it, it has certain outliers. If you go ahead and fitted this one, you will see the models tend to overfit. Now in this case, it had 130, but I think I removed this data originally. So 40 rows I removed. So it became 990. That's what I did. I checked, I will comment it here. I have removed rows where compressive strength falls outside to standard deviation from its mean. So this is something you can easily check. You can always check whether there are outliers in my data. Just when I say about outliers, just imagine this slide. Is that one? So can you see my PDF presentation?
Yes.
Yeah. So if you don't check any of these things, so you might be trying to fit in something like this. You need to check for outliers. You need to check, especially you need to be familiar with data. You need to investigate what sort of data these are, whether there are correlations. Otherwise, don't just go ahead and fit some model. It won't make sense. Is that clear? So this is what I exactly did. I checked the whether there are certain outliers are there. I removed whatever falls outside from the mean to standard deviation to the either side. So with that, I'll give you a 15 minutes break. So we'll start again in 15 minutes. If anyone has any questions, you can ask. Do you have any questions? Do you have any questions to ask or anything to clarify, or everything discussed up to now was clear or not? Yeah, I hope you can see the presentation. Is it there on your
Yes.
screen? Okay, thanks. So I was talking about pre-processing stages, how we make the raw data into a set of clean data and check for there are various steps for additional information. You can check this one, but I have only used a few of them, mainly checking for missing values, whether there were any duplicates, and then checking the outliers and what are the inputs and outputs. This was an alternative way you can do it. So if you only have the columns what you needed, you can just drop the columns of the compressive strength. So I'm taking all the columns except compressive strength as inputs and Y is the compressive strength. Alternatively, you can use this one as well. So it's up to you. Anything is okay. So and another important part is data normalizing. Now you will see the cement, the range of these values 500, and 200. If you look at coarse aggregate, that can even go up to 1000 and 900. So fly ash in the range of 0, maybe 10, 25, and superblast size was also like that. So you will see their values, their ranges differ. Their ranges differ, so that if you give these data to a model, because these data are, inputs are in a different range, it's not easy. It's not easy. I'm not saying it's impossible. I'm saying it's not easy for the model to figure out what are the weights or what are the coefficient for these things. I'm just referring simply a model, could be anything. Okay. So for this one, we normalize these data using maybe something you already know. How you know you normalize and get the Z score of the um, A-level marks, something like that. So you can normalize these inputs maybe to a common range that it becomes convenient to the model to fit. So many of these details will be later, I think, discussed by Dr. Samiru in a comprehensive manner, because especially data normalization. So if you want to transform the data, so far the data we had, we didn't want to transform anything. You saw the compressive strength distribution. It was kind of a bell curve, but if there's an odd shape for the distribution which is difficult to fit, we need to transform it to something that we can fit into. And for that, something like log transformation, you can use those. And there are various techniques, and then data reduction, principal component dimension reduction. That means use only the variables that you need for the prediction, and so on. And we check the distribution. Okay. All right. We'll go with the first model, linear regression. So most of these models are available in scikit-learn. So if you go to scikit-learn website, you will see bunch of models, reach classifier, regression. So if you are going ahead with regression, so let me go to a scikit-learn page. Can you see my Chrome?
Yes.
Yeah. So if I put, let's say, decision tree regression scalar. Yeah, over here it's there. So you will see. So I hope you can see the screen. So here, these coefficients you see within the brackets, we call them model settings or else hyperparameters. So we change them, we tune the model, or we change the model. So what does these mean? If you click the source, you can see. So if you go down, everything is explained here. Max depth. So max depth is the depth of the tree. If none, then model expanded until all leaves, but kind of complex for now. So Let's just not go into that. But for this one, Dr. Samiru, I think, will be explaining bit of mathematics behind these algorithm. Sometimes it can be you will feel like those mathematics behind these models or algorithms are too complex, but it's essential to know them. It's essential to know how a model works. Otherwise, you would not know, or you would not know how to interpret these results. Why your decision tree model is less performing than a random forest model. If you just use ChatGPT to answer that, that will give you a very surface level answer. But if you know how decision tree works, if you know how random forest works, you know why their results, why their performance vary, or what is better. You can interpret it. So if you don't use any of these in your model, so let's say you just use only the brackets, then it will go with these default values. And if you go down, you can find all these codes for the yeah, over here. Just need these few lines from a scalar. Sorry, no, you don't need the data set. What you need is a decision tree regression, and x and y we have already defined, and then the regression or whatever the decision tree you just need to fit into. So you can see they have only used random state. So this random state is just an initiation to get the randomness in the training and testing split. For now, I have used 42, so that it can be a number from 1 or 10 or 100, can be a random number. So 42 means that split I'm using. Whenever I rerun the code will split exactly same rows for the training and testing. It will not be different. Otherwise, the results would be slightly different at each time. That's why we are using the random state. And so if you go back to, so any mod, I think extra tree regression. So this is decision tree classifier. Okay. So if you need the classifier, so mostly all settings, or I would say hyperparameters, are same, but a slight change in the classifier code is that instead of decision tree regression, you are using this term as a classifier. And over here is the classifier. Other than that, everything except the same. And it only makes changes in these two codes, and in the data with you are using, that you will be predicting a class. I mean, if you go back to the notebook, you go to linear regression model. I'm sorry, give me one minute. I'm sorry for the delay. Sorry. Let's go to the notebook. Can you see my notebook, Jupiter? Hello.
Yes.
Yeah. Okay. So, for now, what we did was we opened the data set and imported all the relevant libraries. And one of the key inspections that we needed to carry out was check the statistics and correlations in the data. That will give you a rough idea which models you can use. But I'm sure Dr. Samiru will give you a more comprehensive idea on these things. And then you define your targets and check their distributions. All these, even though these steps taking time, but it makes your model reliable, and what you are doing is correct, and you know what you are doing. And if you then the distributions. So from this, I have in the next cell, I have defined um, two functions to evaluate the model and the plot all results. For this one, I have used R squared and sum of square. So it's same as mean square. It's that I'm not taking the mean of the sum of squared error. If you take the mean of that, it will be mean squared error. So for these two functions are for that one. If you want to change any of these colors and edge color of the dots, plots, and alpha is I think it's a transparency. I'm not sure. I don't remember that one. There was a line and width you can change, and the labels and the plot size. Even if you want to change the font color, you can use edit here and change it, and maybe the X and Y limits. Everything is formatable. And let's get to the linear regression model. I hope you all are familiar with that one. So I went to remember the scikit-learn. Usually, you will see importing the linear regression model from the scikit-learn, which is the first step. But I already have done it over here. You will see the linear regression. I have already imported it and run it. So I don't need to rerun it. But if you have not imported these libraries upfront, so whenever you are using that model, you need this line of code in that cell. So then it should begin with importing linear regression model, and then I'm giving a name. So this name could be anything, even LR or something like that. So you can change it. So that's our model name. Okay, that's a model name. So this is the model I'm using from the scikit-learn itself. So if there's nothing in the brackets, so it will use the default parameters in the scikit-learn. So now I gave a model name. So I'm using that model to fit into X train and Y training data. So I'm not using X test or Y test. So those are unseen to the model. So I'm giving the training data their input values and output values, which are X and Y. to model to learn. So once you do those steps, so model will fit something. And I'm evaluating why training predictions are linear regression dot predict x trail. So if you dot predict x, so that will predict the whole data set. So if you dot predict x test, so that will give you test set of predictions. So here you can keep x train. So that means you are getting the training set of predictions, this part. So testing set of predictions, you will get linear regression model. So which is the model name I have fitted. So predict X test. Is that clear to you? Is that clear to you all? I will anyway import it here. Okay, good. So I will run it and see what's going on. So sorry. So X-train is not defined. So what has happened? Probably I might not have run these. Yep. Yeah. Spray. You don't need to run that. And then evaluate function. Yep. So you can see training sum of square is 69,000, but testing sum of square is 26,000. So if you consider sum of square only, so you can even plot and see a test set. Yeah. So if you consider only R squared value, training set, R squared is higher. R squared is higher. And testing set, R squared is lower. I mean, 58, I would say it's not very good model, but something is there closer to 55 to 60. And sum of square is obviously higher in this model, but drastically lower in test set. So something has happened. So what is your what is your opinion on this model? Is this a good model or fairly good model, or can be? It's very hard to improve a linear regression model because there are only few parameters, and it's linear. Whatever you do, it's linear. So checking the R schedule, is this a good model? Anyone? See. Okay, fairly good model. Yeah, no one can deny that. Yes, it's a fairly good model, but it's not the best. Then why this sum of squares is so if you see the pattern, it's comparable. You would see the compressive strength values between 30 and 40, bit of over predicted. And over here, high compressive strength values are relatively under predicted. So if you consider this variation is going like this, not exactly 45 line, but why does this happen and why we got this huge difference of is sum of squared? Anyone? Yeah, exactly. So imagine this is a sum of squared. Okay, we have training. How many training data? I think it's 700, and it's calculating sum of squared from this all 700 points. But whereas in testing, it's like 200 something. But if you normalize it, say for example, if you want to get the mean squared error, so you need to divide by 69,000 something by number of training data points, and testing sum of squared error 26,000 by number of testing data point, so which will give you approximately similar values. So model is not overly fitted, but it's not a very good model as well. And yeah, it's not a very good model, but because we only get a marginally good accuracy, and it's mainly because we can only develop its linear relationships only. We can't go with higher order terms like compressive strength equals cement squared something plus. We can't go with that in linear regression. For that, we need to use polynomial regression. If we use that, that would be more accurate than this, but I didn't use it for some reason. We'll use it next week. And if you need the model coefficients, since this is an equation, you can easily get the coefficients using this code. And for this one, I think I even plotted it, yeah, over here. So water is getting negative coefficient. So does the results make sense to you? When you increase water, compressive strength decreases. Does that make sense something to you? And when you increase superplasticizers, it has a relatively good impact on the compressive strength. It's more sensitive to superplasticizers. If you see a smaller increase in superplasticizers will increase the compressive strength by a significant margin compared to the remaining variables. This is overall trend only. Okay, this not saying this is all true for all the rows. This is the overall set of coefficients we got. So which which shows their feature importance. Are these results okay with you, or does these results make sense with what you know, or if anything disagrees? If anyone disagrees with that, let's say someone argues, okay, this coefficient should not be this much low or maybe this much high, or does these results make sense to you? And remember, it was not a pretty good model. Since we obtained only 0.5%, now we know, okay, the linear regression doesn't work properly. Then again, back to basics. What I taught, use the simplest model that gives the best accuracy. So now we can get rid of linear regression for the moment and try fairly a better one. Let's go with the next one, which is KNN. So even though the name is like complex to you, sorry, before that, I will show you how, if you want to save the predictions, let's say now if I want to, let's say you want to save these predictions for all the data set. So what you need to do is data frame and arrange a new column. Let's call it LR. So in that Excel sheet, in the data frame, you will see a column named LR. So our model name is linear rig dot predict. Now we are using the whole set because DF is the whole data frame. So I do that. If you want to see the data frame, you can see now. You will see the predictions over here. This is a compressive strength original value 6150. For the 40, it has predicted 58. So all the predictions are now in the data frame. If you want to save this one, you can just save it by data frame 2, another CSV, name it, let's say predictions with linear regression.csv. So once you do it, so you will see in the same directory a CSV with the predictions and inputs and output, everything. Clear? Is that clear to you guys? Okay. Yeah. So when we'll go to the next model we can use, which is the k nearest neighbor. So k nearest neighbor, as the name says, works based on the neighboring points. Can't see. Someone said that he can't see the link of attendance of Google Sheet due to some error. Please confirm. Chamod, if you can check. Okay. So I'm using name as KNN. KNN. So this is again, I got it from the scalar. So there are a bunch of hyperparameters in their website, but I only use number of neighboring points. And there's another one called distance, how they calculate the distance between these points, which I will get back soon. Let's go with first an example. How does that work? I'll give you a quick presentation. Can you see my presentation?
Yes.
Yeah. Okay. So all the things I have marked in the presentation itself. The reason I didn't went through linear regression a lot is Dr. Nihash has already covered it. And what are the important lines that you need to remember? So model evaluation, I have only used sum of squares error and R squared. So this model evaluation is mainly important for two aspects. First, they show you how well the model have learned the pattern inside training data, and it will show you how well they predict for new or unseen testing data. So those are the main two components why the model evaluation is important. So in the model evaluation, so these matrix, mainly statistical matrix, can be divided into godness of fit matrix and error-based matrix. So godness of fit matrix like coefficient of determination or is a coefficient of correlation. So R squared, we call it coefficient of determination, which can go from 0 to 1, but make sure you check what is available in a scikit-learn R2 score, which I have used. It is not the same formula as far as I think, because that R squared can be even negative based on the equation. I'm not sure. Just because if you get R squared like 0.3, -3 or -4, don't be confused. It's just the difference between two formulas they are using. It's scalar. Whatever the R2 score used in scalar can be even negative. I haven't checked that one, but just keep that in mind. It's for the correlation, which can go from -1 to +1. So if it is -1, so that we call perfect negative correlation, and on the other side, perfect positive correlation. And the error-based matrices are mean absolute error, and there are a lot more. Okay, you can check, especially in the literature or machine learning based studies. There are a lot. I mean, squared error, and even I have not mentioned sum of squared. So I have used this one, this observed minus prediction to the squared, the summation of that. So if you divide it by number of data points in that particular segment of maybe training or testing, you will get the mean squared error. If you take the root of that, you will get the root mean square error. Yeah, we'll go to KNN first. I will give you an example. Imagine we have 9 people. Their age is like this. And salary, they have given 50, 55, 70, 80, 85, 100. And this target is whether they are all applying for a loan, and whether the loan is approved or not approved is the target. So can anyone say now, even though I made this as a regression, sorry, it should be actually classification terminology. So this should be actually classification. Okay. So if we are predicting a class over here, if you can correct it, just make a note. Didn't notice that. So we want to predict whether the next guy's, ninth person's loan is approved or not. Even though it is classifier or regression, their working principle is same until the last step, where classifier will be taking the majority voting and the regression will be taking weighted average or something like that. So now, make sure you correct this one. This should be classification. I mean, it's because the problem here is a classification. Okay, problem here itself is a classification, but we are doing using it for the concrete compressive strength model, which is a regression problem. Still, we are in a supervised learning. So now, back to the problem. We know their age, we know their salary, so we have two inputs. The person is not an input, it's just an index. So the target is whether their loan is approved or not. So I'll use one color for the approved and another color for the loans that are not approved. Now this is scikit-learn, which I have told you already. So if you go to scikit-learn, all the hyperparameters are there, number of neighbors, and this is the distance matrix. So how they calculate the point distance between these points. There are Euclidean based distance and Minkowski and some other Manhattan. There are few 4 or 5 or 3 or 4. I don't exactly remember. So if you read for more information, this source, that will tell you what these parameters mean. And back to the problem. And sorry, for your more information, I have given here how to optimize these parameters. For now, we are not focusing on these methods. I think Dr. Samiru will give an introduction for these methods. This is how we are going to optimize, because we can't, you can't just randomly pick these numbers. For example, for number of neighbors 6, you will get a better performance. You will get you will get a poor performance again for number of neighbors equals to 8, and maybe the matrix is different there. So you need to optimize these, but it doesn't mean that you need to optimize all of these. First, you need to know which hyperparameters matters most and try to optimize those. And those optimization methods are presented here, but which you don't need to worry for now, because the data set we are using is a bit of a simple problem. Okay. Okay. So this is the difference between classifier and the regression I have mentioned there. So now I have plotted their age and salary. So blue color dots are, blue color means their loans have not been approved, and red color is their loan has been approved. So the X point, we need to figure out whether it will be a red or blue color. So what now KNN does is it looks at the neighboring points, which you define by number of neighbors. If you say 2, that will look at 2. If you say 3, that will look at nearest third neighbors based on the distance. Okay, it's just like this. Let's imagine in your class there are 4 students. Okay, let's say those are those are the highest marks in the exam. The batch top, second, third, and the fourth guy you don't know the rank, you don't know the mark, but just because they are with, if someone asks you what will be the marks of the fourth guy, okay, you know the marks of all other three people because they are batch top, second and third. There are marks like 99, 98, 99. So the only clue you have is look at their neighbors. Okay, this guy has 99, this guy 98, this is 99. So only prediction you can make is because their neighborhood is having marks like that, you will assign something like, okay, the fourth guy should have 98 or 99. Someone should see this as not exactly a learning. It's just looks at the neighborhood and gives you the estimation. So now what we can do is we can first calculate their distances. What I do is now person A, age is 18, salary is 15. So it's only we are working in a 2D input space. And their distance, I'm using Euclidean distance formula, which is x1 minus x2 squared plus y1 minus y2 squared. So I'm distance, I'm getting this one. So likewise, you can calculate each Euclidean distance for each person with respect to the target point X. Is that clear to you, or is it complex? Is this clear to you, or do you want me to repeat? Sorry, I can't see your messages. Is that clear to you? Okay, two is it clear? Others? Because it's very important, I need to make sure that you all understood that concept. Everyone? Okay. So now what I do is I rank them or sort them based on the distance. So E is the closest neighbor to the target point. So if you say one neighbor, which you should not do because you can't take a decision based on one neighbor point. So if you say the number of neighbor points over here is 2. So this will use 2 nearest neighbors. If you say 3, that will use 3 nearest neighbors. And based on their majority voting, that will give you the prediction. So if you use K as 2, so their majority voting is yes, loan is approved. So you will say the X guy, his loan will be approved. Now if you use 3, K equals 3, okay. One is they are saying not approved, but majority voting again saying loan will be approved. But if you go for higher K, that will say K will be not approved. But you will see when you are going for more, when you increase K, so those are no longer nearest neighbors comparatively to these neighbors. So you need to make sure what are these parameters, what is K. I should not just increase K and get a good accuracy. It doesn't mean anything. In the regression, this will be taken based on weighted average because there will be a numeric value. So you need to know how does KNN works. Do you understand that point? It's just look at the neighborhoods and based on their distance will give you a prediction. Do you understand that? This is exactly same behavior when you are using KNN to fill missing values. So it will see, it will check let's say, we'll go to this point. So over here, just forget about this line for now. So now, let's say this value, okay? This row, this white color row. So you will see, let's say this compressive strength is missing. So if you need so let's say this is missing, you don't know it. You need to impute it or interpolate it. So if you use k nearest neighbors, it will look at maybe nearest one or two neighbors. It doesn't mean that closest rows. Okay, nearest neighbors means okay, cement content closer to 380, blast furnace like closer to 95, fly ash closer to 0, water content closer to 228. Likewise, and based on those rows, and though they have, we know their predictions. We know the compressive strength in those rows, those neighbors. So based on those neighbors, either you can take weighted average or just the arithmetic average as the imputed value. But when you use many neighbors, that can be even deviate from what it actually be. So just remember, increasing k does not guarantee you that it will be accurate, okay? It's just number of neighbors that you are looking at. If you look at the wrong neighborhood or neighbors who are located away from your neighborhood, it just doesn't make sense. How to select k value? Yes, it's an optimization. As I told you, you need to optimize all these hyperparameters, k and distance. We can't guarantee, I mean, by looking at the data, you can't just guarantee, I mean, just predict or just select this is the k value. Say, for example, you can do a trial and error way with a specific k value. Maybe you select 10 or 5 and see their values behaving. If you don't get anything meaningful, then what I would do is I would select a loop from k values ranging from 2 to 20, and run 20 models and see their training and testing values. And from that way, we can optimize what would be the best k value. Did I answer your question? You need to check the evaluation metrics, training and testing scores, and not only the scores, their plots as well. So R squared can be closer to 1, having deviations in either side, the perfectly negative side and positive side, having cancelled those out because of the square. So you need to make sure you check the plots as well, not only the statistical metrics. Visually, you should observe what has happened to the prediction, why the model predicts this way, what happened to the higher values, lower values, everything should be checked. And then select a k value. And it doesn't guarantee that like k value is the only hyperparameter. So let's say distance, then it becomes you need to optimize 2. So that's for that case is what we are using these methods. Let's say you have 2 hyperparameters to optimize. So we'll select, let's say this x1 is k, x2 is, let's say, another value. Let's call it alpha. So we give fixed values, let's say 1, 2, 3, 4, 5, and x2 is, let's say, 2, 4, 5, 6, 7. And it creates a grid for all these models, in this case 25 models. So it evaluates all 25 models, and based on those you can select the optimum model. Is that clear to you? So it's a bit of optimization. Once again, Dr. Samir will look into this one. Who asked that question? Mayuranki. Is that clear to you? Okay. So he will explain why this grid search and then random search, if not Bayesian search, what are these pros and cons? Mainly those are hyperparameter optimization methods. Now, we'll go to the notebook. Okay, you can see my notebook. So I use 10, even though I commented k equals 5, I use just random number 10. Okay, let's see what will happen. Oh, sorry. Yep. So R squared is compared to linear regression fairly better, even the sum of square. Let's just, for fun, just increase and see what will happen. 66, almost comparable. Let's just reduce and see. Maybe 6. Yeah, even that's kind of better, but the gap between training and testing is a bit large. But you need to properly do an optimization using distance and neighbors and everything and come up with a solution. That's how you should do it. So again, the same principles. This is what I obtained from the scikit-learn itself. All these parameters are there. So for the k-nearest neighbors, I usually use number of neighbors and the distance metric. It is usually enough for civil engineering problems that we encounter. So, and then again, this is regression. Okay, again, back to compressive strength problem. Regression, I'm fitting into training and training data set and predict to training and testing and compare it. Okay. Now, this is something important. So these are original data. I didn't scale these data. So I told you model, it would be convenient for model to compare, learn and determine it weights or coefficient if all the inputs are in a similar range. So I'm using min-max scaler. So what it does is min-max scaler for a particular input value, let's say xi. So we deduct its minimum value. If it is cement, we are deducting the minimum cement content from that and divide it by the difference between maximum and minimum cement content. And this is only for the training set, okay? Minimum and maximum of the training and a training set. Otherwise, if you do it for the full data set, data can be leakage because some information in the testing data are also there in the training data. You should avoid that. We should never ever avoid testing data in the training data set. That we call data leakage. Okay, that should not happen because model should be tested for unseen data that the model has not seen. If you have the same mix design in the training data set and the testing data set, you need to remove it from one set. So again, back to scaling. So why scaling matters, I have given here. Scaling puts all features into the same footing. So it's easier for to learn. Doesn't mean that it's impossible without scaling, but with scaling it's easier, and sometimes most of the time the models become more accurate. So scaling is very essential for models like KNN, SVR, ANNs, which are kernel based methods. Okay, scaling is not important for decision tree based models. The reason we'll learn in a moment. Decision tree models works on impurity of the data. Doesn't matter whether you scale it or not. Even if you scale it or not, you will end up with the same result. So you don't need feature scaling for or normalization for the tree-based models. I'll show you why. But especially for neural networks, this does make significant sense, the results. So I have developed SVR, but I'm not going to teach you how SVR works because it's a bit of mathematics. I would say bunch of mathematics, which will take time. And I hope that will be explained properly by Dr. Samiru about support vector regression. So this is another regression model which is available in scikit-learn. So don't worry about these parameters for now. Those are the hyperparameters in the support vector regression, which is available on scikit-learn. So what I want to show you is, so this is, oh, sorry, did I scale it? So it's ran it. Okay. So I fitted the support vector regression with this unscaled data. So this is scale data. And let's see how it works. So you can see the unscaled data training set. So you would see bit of a scatters and R squared only reaching up to 0.6 and training test set even 0.63. It's not an overfit. It's good, but it's not a very good model. But over here, it's min-max scale one. Training reaches up to 0.86 and testing is 0.85. So it has been improved just from the feature normalization. You can see the difference. So I used all same parameters, same hyperparameters. It's just that one is using unscaled, the original training data. So the second model is using training scale data. How I did that was I used the scalar as min-max scalar, and then I define X training scaled. So you remember this one, right? X train, which was our original training set. So I'm defining something called X train scaled using this scalar and fit transform function using the training data. And same I'm doing for X test as well. So now we have something different for originally we had X train and X test. We didn't do this for the Y, okay? We only normalized X, okay? We didn't want to do it because distribution of Y was something fittable. We didn't want to normalize it or we didn't want to transform it. And now we have X train scaled and X test scaled. Okay, we have this. So now I'm using those first original X train and Y train to feed this support vector regression. So parameters, again, the same process as I explained in the linear regression, and get their performance through the evaluation model function, which I originally defined it beforehand. And I'm doing the same thing for the support vector regression model using scale data and original Y. You will see I didn't scale Y at all. It's just that I did scale only X train and X test. So with With that, I'm getting something like this. So when you get R squared value, it's important to know that you know the model is overfitted or something like that. Let's compare. We are getting R squared value for training. Let's say 0.999 and testing 0.96 or 95. And this is the second model. Let's say we are getting R squared. I'm only considering R squared value, but having said that, you need to make sure to and check the mean squared error and other error matrices as well to properly check the model is overfitted or not. I'm only doing this for the time requirement. Let's say I'm getting 0.86 and testing 0.881. So what are your thoughts on the best model? What is the best model from these two? Model A or model B? If you are to select one of these models, what would you select? And why? Who say model A is better? Who say model B is better? This is only the R squared value only, okay? Anyone? No one? Okay. One said model A is okay. Others? And can you explain why A is better? Okay. One said again A. Any reason why A is better? Okay. R2 closer to 1. Fair enough. Okay. This is the same way I used to look at when I learned these models as well. Now, just give me, just select the error of this. Just forget about everything. Error of this one. No, I mean, you don't need to consider about SSE. Yes, you need to check that, but I only have R squared value given just as a fast impression. So error of this one, 0.99 means error is 0.01. Is that correct? From the R squared to the 100. Sorry, 1. So error in testing is 0.05. Over here, error in training is 0.14. Over here, error in testing is 0.19. What's the percentage of increase error compared to the training in testing? 1 is to 50. What's the percentage of? Is it 500? Oh, sorry. I can't even do the math. Sorry. How much the percentage increase? When 1 becomes 50? What's the percentage of increase? Yes, 5,000, right? 5,000 percentage increase in error. Over here, it's how much? How much the error increased? Yeah. Is that 136? 14 becomes 90. Is that 136? Should be lower than that. 14 becomes 19. 5 over 5 over 14, right? Yeah. How much is that? Check. It's 35%, right? Is that? Am I correct?
Yes.
Yeah. So now again, I'm asking, now, what's the best model now? Is that A or B? The first model A, when it comes to testing, the model error has increased from 5,000. Now in model B, it's only 35. Yes, exactly. Model B is the better one, even though it's slightly less accurate, just because it's a very good learning curve for you. Just because the training error, training R squared, or I'm only using R squared for now, is closer to 9999, and you should see it from the 100. Okay, what's the error now? If it's a good model, the testing R squared should be closer to 998 or something like that. Otherwise, if it becomes 95 or 97, that indicates model is going to overfit, or else it has already overfitted. Okay. Yes, it has fairly good accuracy. I would say very good accuracy, but the model is overfitted. So if you explain or if you use an overfitted model, results would not be reliable, because this might be due to mainly due to, okay, your data has slightly off, maybe an outlier or a kind of an outlier. Model has perfectly fitted to that. That's why it has gone to 99. So whenever you get 99%, now onwards, you should not be happy. You should be checking why I should get 99. Is that correct? Is that something wrong? Whenever you get 99, so back then I was happy. Okay, it was 99, perfect. So now if I get 99, I'm really being careful. Okay, whether something has happened, whether the model is overfitted or something like that. So this gap makes sense. Okay, if its training was like 95% and testing was like 92, 93%, so it's like from 100, it's 5 and becomes 7. So it's fairly okay compared to this. We don't have exact guideline to define an overfit. We can say only it's going to overfit, or else that it has already overfitted. So make sure when you see maybe in a research paper, someone say its training is 999, clearly it's an overfit. 100% sure. Most of the time it's an overfitted model. If they are testing, its score is very low. So you should avoid those things. And if I wanted to use a model out of these, I would 100% go for model B. Even though it's less accurate, I would go for model B. But it doesn't mean that we can't optimize model A. We can optimize, and there are methods to get rid of these through optimization, especially if you use models like XGBoost. There are regularization parameters. You can get rid of these overfitting. So again, back to the problem. So I have shown you what's the impact of feature normalization, especially for models like SVM and KNN as well. You will see a slight improvement in KNN if you use a feature normalization, or sometimes you might not even see. It depends. But most of the time, support vector regression and ANN, I have seen. Um, uh, I have seen a good improvement. Yeah. So now our last one for today is decision tree and regression. Chamod, how long do we have now? From
So actually, the time is
oh my God, Hmm.
until
Is that
12.
okay?
So you can do around uh, additional
No,
10
if
minutes.
okay, no, no, if I go for 10 minutes, it's not enough for decision tree. So, and then I'll be taking Dr. Samiru's time as well. In that case, shall we wrap it from here and start next week? Anyway, we are going to use all these models in next week as well. Uh, is that good? Is that okay with you guys? What do you suggest? Because I need to take a bit of time to explain. I mean, explain how decision tree works, and then go with decision tree and random forest and finish it. So that will take more around 20 to 30 minutes. Uh, are you guys okay to wrap it up here and continue with Dr. Samiru? Hello. In that case, we'll wrap it up and we'll start from the decision tree and random forest, and then we'll use up to neural networks during that session as well, and with explainability. Is that a good plan? Okay. Okay, then, Dr. Sumudra, I'll hand it over to Dr. Samiru if he's yeah. While we are handing things over, so if you have any questions, you can ask quickly.
Excuse me, sir.
Yeah.
So you can have additional 20 minutes, sir.
Okay. I'll go ahead with that. Okay. Okay. Let's go with the decision tree then. So now, this is the simplest tree-based model that we can use, which is which has a logic-based tree structure. Say, for example, the tree, when you have data, the algorithm works based on the impurity of the data, which is why I told you we don't get any benefit. I mean, we don't get a good benefit from the normalization, because the normalization doesn't change the impurity. Or else, you will see if you normalize the curves, the distribution remain unchanged unless you transform the data, right? So so it starts with a node called root node. Okay. So it selects a variable. So how it select the variable, I will explain it later. In this case, I had three inputs in this PDF, as you can see. So x, whatever the inputs where x over h is less than 9.5, all those samples, so out of these 6,400, are moved to this node, which we call an internal node. And whatever the samples where x over h is greater than that will be over here. Okay, so like that, it keeps dividing, do these binary splits based on the impurity of data, uh, and selecting what is the splitting criteria at each node or the variable. I'll show you how we select that one, y over h or x over h or what. And finally, so it keeps dividing these data. If you say the tree depth is 2, so this will be your terminal nodes, which you call leaf nodes. Whatever the points over here, tree will just give the average and give as the prediction. So what they do is remove the large variances from the data and isolate a small local variance. Okay, the groups with smaller variances and isolate them. So mainly based on impurity of the data. So I will show you one example in the notebook. Sorry, where did I go? Okay, so if I go to a decision tree, now again with sklearn. So in the tree-based models like decision tree, depth is an important parameter. So how long uh, you are you are splitting these data into how many depths. Okay, so random state is again a random seed, as I explained earlier. So again the same things, fitting the training and test training set and checking the predictions. So with depth of 3, I have obtained 60 and 45, not bad or not overfitted, but it's not very good performance. I would say moderate performance. Let's see what will happen first. Okay, first we'll try this one. Okay, depth is 3, and now you can see something significant. You can see these predictions are not like scattered over here. Like it's like y equals alpha lines. Can you see that? Are you guys seeing this one? Can you see this pattern over here? It's like whatever the compressive strength value, it will predict a constant, something like that. Is that clear to you?
Yes.
Okay. So why does this happen? So now if you look at the tree structure, now I have um okay, now I have drawn the tree over here. So this is the tree. So how they configure this edge or cement at this each split criteria, we can discuss later. I will show you because it's at the end of the code how to select that one at this each step. So let's figure this is the trained decision tree. Now you are giving a new data set with new data point which you have age. Okay, first the tree look at the age. Oh, if the age is less than 21, it will go to the left. Okay, that input set. Okay, if their age less than 21, that will go to the left side, and from there onwards the tree will look at the cement content. Okay, tree, if the cement content is less than 354, that will again go to the left margin. Okay, Then there onwards, tree look at the superplasticized. I'm talking about this leftward branch. Okay. Okay. Superplasticized the content. If it is less than 6.5, it will end up here, that point. So that's the leaf node. So this depth has a this tree has a depth of 3 first, second and third. This is the term. So the value over here is 15.3. So when you were training the algorithm, so whatever the values came here, whatever the data points came here, their average compressive strength of is 15.3. So whatever the new data point comes to this leaf node, the model will predict the compressive strength as 15.3. Doesn't here age can be 2 days, 7 days, even 10 days, all goes through this direction. Cement content less than 345, all data points goes through this location. If the superplasticized content is less than 6.5, all those data will be in this leaf node and will be predicted as compressive strength 15.3, which is why you are observing this variation. Can you understand that? It's a logic based tree. Did you understand that logic or not? So the prediction is actually the average in the leaf node, which is 15.3. If something comes like, okay, age is greater than 21, it will go through the right path, and then they check the cement content. If it is 330, less than 313, or let's say greater than 313, it will go this way. Then the tree look at the water content. Water content is less than 178. Everything going through this path will get the prediction of 58.1 megapascal. Is that clear to you or not?
Yes, clear.
Okay. So let's try increasing this depth. What will happen? Just go with 6. Now you will see that scattered nature bit reduced. Why? The data are far more splitted. If you draw the tree, tree will be large. I don't know whether it will be plotted or not, but let's give a try. Why not? Yeah. Now even those whatever the leaves in these core will be further splitted based on minor variations, minor variances. So tree will start separating more finer variances into smaller groups so that your prediction will be becoming more accurate. Is that clear to you? So with the depth, but still you will see that variation kind of y equals alpha. Still, I can see that. Now, something to concern. How many data points we had? Around 900, let's say 1000. So how many leaf scores now have? So it's a 1, 2, 3, 4, 5, 6. Okay, 2 to the power 6 is we have 64 leaf scores. Okay, so that 2 to the power n, so which is n is the depth. Okay, 2 to the power n should be sufficiently sufficiently lower than the number of training data points unless you do pruning. I will explain what is pruning later. So 2 to the power depth, that's some common thumb rule I'm using. 2 to the power n is sufficiently lower than the number of training data points. The reason is let's say I have 100, I have depth is 10, let's say depth is 10. This is probably going to get overfitted, or depth is 12, let's say. See, 99, 82. The model is overfitted. Why? You will see. So this is, I think, testing, yeah, test set. So it's overfitted. I haven't drawn the training set. It would be like a perfect line. The reason is not because the model is accurate. Now we have leaves 180, 120, more than 100 and, sorry, 10 to the power 10 to the power 12 is, sorry, 2 to the power 12 is 4,000 leaf nodes. Okay. But we only have 100,000, or sorry, 700 training data points. So there's a chance that only there may be only one data point in that, in a particular leaf node. So the tree takes the average from a one data point, which is extremely sensitive, which is why your model gets overfitted. Okay, so you need to make sure depth is an important parameter, but you should not overly increase it. You should optimize it, but you should make sure when to optimize, how to optimize, what's the safe number to optimize it. In this case, I will be using maybe 6. Yeah, it's still, I wouldn't say a good prediction, because 87 and 78. We need to check the other error matrices as well. But if you increase depth, because I have seen in many of the papers and everything, depth is 22. The model has only 1,000 training data. So clearly, that's, I mean, don't know what to say. It's overfitted already. Depth is 22 means it has leaf scores unless you prune it 2 to the power 22. Imagine the number. And when you are dividing each one in each way, or maybe only one or two samples will come to a leaf node, and you are getting the average of that as the prediction, which is extremely sensitive. So pruning means we can cut the low information branches. I think Dr. Samir will give an brief explanation on that, because I'm not a very good expert on pruning, because I myself have not done much of pruning, but I know the concept only. That way you can reduce its overfitting. But having said that, you should know how the tree works. It based on the impurity, so it keeps dividing data to binary splits, and based on the depth, and at the leaf node, it will take the average as the prediction. That's it. Now, if you use random forest, so now we are getting predictions 87 to 78. So I'll use random forest again, is a tree-based algorithm which makes a forest of decision trees. I will show you how it's created. Now I'm using random forest depth. So this 100 means number of trees, which you call number of estimators, which is in the scikit page, max depth. So we call these methods as tree-based ensemble methods. Ensemble methods. Models like random forest, extreme gradient boosting, light gradient boosting, and there are a few of those, I think cat boost as well, but it's for mainly categorical boosting, categorical variables mainly, but you can use it for regression as well, are called tree-based ensemble method. Ensemble. So it's a collection of trees. Okay. So now if I go ahead and train this one, it's the same process. Random forest, you will see this bracket is nothing but the hyperparameters which were in the scikit-learn. So I have given these comments just for you to understand what are those. And then fitting is done in the same way. In the same, I will use the same depth. Let's see what will happen. Yeah, 91, 86. Not that overfitted, but you need to improve it. And you will see it's fairly better than the decision tree at the same depth even. Why does this happen? So now, what does these random forest does to improve its predictions from compared to the decision tree? With that, I will finish. Just let me explain that part. Now, if you can you see the slide? Can someone tell me quickly?
Yes.
Yeah, okay. So now we have the original data set, number of training data point 1 to n, and number of inputs and y. So this calls something bootstrap sampling. That means we are taking random rows, okay, random rows from the original data set, but the logic is same row can be taken more than once. But finally, it will be again the number of original sample rows. Okay, so the logic is randomly selected, but same row can be selected more than once. And for the inputs, if there are 9 inputs, we can selectively get inputs. We can go for three inputs, 4 inputs, or else 9 inputs, and randomly sample that. It doesn't need to be exactly 9 inputs. What it does need to be is like number of samples, rows should be same. Yeah, I'll share the presentation, sure. And we call this bootstrap sampling. For this each sample, each new data set, okay, sample from the original data set, we fit a decision tree for each data set. So if you have, so this is what we call number of estimators. So that means if that's 100, so there will be 100 trees. So finally, the predictions. So when you give a new data point, the prediction in a certain tree, okay, certain tree, decision tree 1, 2, 3. So there will be 100 predictions, like the one I showed you in the decision tree. It's just only one prediction taken out from the corresponding leaf node. Now there will be 100 prediction. Finally, we are getting the average of that. Because of this averaging, the predictions become better. The reason is, let's say there's an erroneous data point or something that you missed. When you are doing the bootstrap sampling, that feature or that row sometimes completely off from that tree, completely not visible in that sample. So that tree will have a good accuracy, and the next tree will have that erroneous data, or some trees might have, some trees might not be having that. Because of this one, because it's randomly selected features and subsampling technique. So once you are getting the average of all these trees, the predictions become fairly better. And I have seen from what I have been using, the random forest model, I would say 90% times works better than decision tree. Works better than decision tree, but for smaller data sets, I have seen decision tree and random forest are comparable. Okay. And even much improved versions of these are like XGBoost, and gradient boosting, histogram gradient boosting, and cat boost, which I will not explain. But now you know why decision tree gives these prediction, what happens with the depth, and why random forest improve these predictions. I didn't go much on these mathematics, but this is the conceptual framework as I understood. So with that, bootstrap sampling means you are randomly selecting rows to sum it up to the number of samples in the original samples. The logic is you can select m number of features. It doesn't need to be original number of input features, but same row can be taken more than once. Okay. This is how random forest algorithm works. And then that's why the predictions become more accurate than a regular decision tree. So you need to know, I mean, to explain these things. So because especially 5 more minutes, last few minutes, like decision tree at lower depths, we call it because you can see can you see my presentation? So here the decision tree, you can see what's going on. So we call this, the model is interpretable. Decision tree at lower depths, interpretable. So model itself can be interpreted, and even linear regression. But when the depth is increasing, it is no longer interpretable. We need explainability methods to explain the model output and how the inputs affect model outputs, which we can do in the next week. Are you okay? Everything's clear to you? In that case, we can hand it over to Dr. Samiru if there's no question. Chamud, are you there? Like,
Yes, sir.
yeah, shall we hand over to Dr. Samiru then?
Actually, now we are having the lunch break.
Oh, okay. After that, okay, all good. Okay, you can have the lunch break, and then we'll continue the session with Dr. Samiru, and we'll continue the remaining part in the next week session. I'll send you the presentations. Thank you.
Thank you, sir.